start over.
All right, well, today we are going to do Chapter 8, Acids and Bases. Before we do that, on Wednesday we are doing lab number 8, which is empirical formula for potassium alum, it's called. Potassium aluminum sulfate hydrate. What we're going to do is determine exactly how many waters there are per molecule. We know all about water now. When you crystallize an ionic compound from water, sometimes you can include waters of hydration. This is a crystal of alum. That's potassium aluminum sulfate. And this one, I believe, has 12 waters incorporated per unit. This is based on the X-ray structure. We have potassium here, aluminum, and then we have 2 sulfates. Surrounding all of this, we have 12 waters. And as we know now, water is a very polar molecule. It orients itself around the ions and gives us a very stable pH. Now we've seen crystal hydrates before. Very early lab we took copper sulfate pentahydrate. What we did was take this and we heated it. It changed from a lovely blue solid into a nondescript white powder as we simply drove off the 5 waters. As you were cleaning up, some of you noted that when you took the white powder that was in the tube and added water to it, that it went back to the hydrated form. Lots of crystal hydrates in nature. This one is radioactive. It has calcium, uranium, silicon, whatever. Nickel nitrate, lovely green. Copper chloride or cobalt chloride has actually found a market for itself. The waters here are held very, very loosely. And so if you take this and you place it in different stages of humidity, it will undergo spontaneous dehydration. This is the hydrated form, and we get a nice lovely blue for the dehydrated. What you do is you take this stuff, you put it on a little card, and depending upon the relative humidity, it will change color. So kind of an interesting thing. For alum, again, what we're going to do is figure out X here. That's the number. It can be anywhere from 12 to 24. In the lab, what we're going to do basically is determine the empirical formula. We're going to take the potassium alum, heat it up gently. When we do, the water will be driven off. We will determine the mass of the anhydrous form. From that, we'll figure out how many moles of water went off, how many moles you have, and you've got the empirical formula. Kind of a simple, straightforward lab. Most people do very well with it. Any questions? All right, acids and bases. We're going to talk about the concept of autoprotolysis first. Ionization of molecular compounds, then move on to strong acids and bases, conjugate acids, concept of neutrality, and finally, pH calculations. So, for pH calculations, you're going to need your calculator. So if you want to dig it out and warm it up, type in 4,000. Now I suggested that people figure out how to use the log and 10 to the x functions. Hit the log button for 4,000. You should get 3.6. If you, depending upon your calculator, you could take the 3.6 as it stands, hit 10 to the x, you should go back very close to 4,000. Those are the two functions we're going to need today. Any questions? All right. We talked about electronegativity. We talked about water. We said that water had two polar bonds that generated a molecular dipole right up the middle. Then we have the bottom part of the molecule here is electron deficient. The top part by the oxygen is electron rich. We saw that this polar molecule, the fact that water was polar, is what allows it to take ionic compounds like sodium chloride, dissolve them. It dissolves it and stabilizes the charge by bonding for the anion, the positive end towards the anion. This we have the negative end towards the cation. This disperses the charge and makes things stable in solution. Well, water can not only interact with ions, it is a polar molecule and can interact with itself. We have two positive hydrogens here. We have two lobes of electrons up here at the negative end. If we bring another water molecule in, something like that, we can form what's called a hydrogen bond. Hydrogen bond is a covalent bond, but it's about 5% the strength of a standard covalent bond. But if you get enough hydrogen bonds, it makes a huge difference in the molecule. So we can form one here. We can bring another water molecule up here, form another one here. Remember, we have two lobes of electrons on the top. Bring in another water molecule on top, and we can actually form two hydrogen bonds on this side. This is a representation of what it actually looks like. One water in the middle, I've placed four around it. This guy over here is actually a calculation. What we did was ask the computer to take a cluster of water molecules and show the hydrogen bonding. If you note, like look at these guys here. This one right here, this oxygen, very tightly hydrogen bonded here and here. These are all very tight hydrogen bonds. Very, very stable structure. But this structure itself, although it's stable, lots of inherent energy, it is very dynamic. This structure rearranges about 1 billion times a second. This is a little video showing that calculation. The little purple lines that keep popping back and forth are hydrogen bonds for this cluster of water. Now, as you watch this in amazement, imagine it going, first of all, 1 billion times faster. And secondly, if you look carefully, every now and then you'll see an odd water molecule. This is an OH, hydroxide anion. There is an equal number of hydroniums in there as well. That's H3O+. These are arising by the process of pyrophotolysis. Basically, it goes something like this. we have water molecules that are actively hydrogen bonding. We've seen that this can be very close to the other one, right? If one of these active water molecules gets, say, bumped, gets a tiny bit more energy, what can happen is that this hydrogen and this hydrogen bond can move along the bond from one oxygen to the other. When we do that, we form hydroxide anion and hydronium. Now again, this is all happening on a billionth of a second time scale. This can hand it back, reform our two waters. These can go back and forth and back and forth and back and forth. The bottom line is, if you have a sample of absolutely pure water, autophotolysis will go on, and there will always be an equal number of hydronium and hydroxide ions. The concentration of these, we know, to be 1 times 10 to the minus 7 moles per liter. Small extent, but very important. This is worth remembering. Pure water, hydronium and hydroxide are always there at 1 times 10 to the minus 7 moles. You noted, or you may have noticed, last chapter we talked about electrolytes. We said if you took a non-electrolyte dissolved in water, instead of getting a 0 reading for the conductivity, we had a reading. That's due to autophotolysis. In this water, there's always hydronium and hydroxide. Now, these guys are very highly charged ions, hydronium and hydroxide. The reason that we can form these in solution this easily is that the water that surrounds these stabilizes the charge. Let's look at the hydronium. H3O plus. That's the top. Instead of being red, it's light green. Big blue bottom on this from the side. If we do what we did with the sodium cation and surround the hydronium just with 3 waters. Remember, the hydronium is big and blue. Our 3 waters, just the 3 waters, are able to disperse the charge enough to give us something like this. The oxygen here now has a yellow cap instead of red, but still we have a great deal of dispersion. But water doesn't just live in groups of 3s and 4s. As we saw, water is a large, continuous structure. If I take and do this same thing, putting my hydronium here, and I've surrounded it here with 8 waters, we can, again, this is the hydronium, what it looks like. If we go and calculate the electrostatic potential map for the whole cluster, we get something like this. The hydronium in the middle now has a nice red cap on it, and the blue, well, you can barely see any blue at all. Totally effective at dispersing this charge. Amazing. Any questions? Well, if water is capable of breaking an OH bond, it's also capable of interacting with polar molecular compounds and breaking their bonds as well. For example, we looked at our friend hydrogen fluoride. We said in hydrogen fluoride, we have a very positive end, a very negative end, due to differences in their electronegativity. If we take and put hydrogen fluoride in water, it will line up and it will hydrogen bond very effectively. Just like with water itself, if this complex gets just a tiny kick, tiny bit of energy from somewhere, this HF bond will break and we will form hydronium and fluoride anion. We have broken the covalent bond and made hydronium ion. This process is, of course, reversible. It can go this way and that way at the same time. In chemistry, when we have a reaction that easily goes both directions at the same time, we call that an equilibrium. We use a special double arrow to indicate the equilibrium here. What this tells us is that HF and water are giving hydronium and fluoride very, very rapidly, and reversibly. You make it and you go back. Excuse me. Now, things that dissolve in water and form hydronium ion are termed acids. So, in our discussion of acids, we are going to discuss two types, strong acids and weak acids. Actually, we are going to discuss weak acids very, very casually, because weak acids are kind of the realm of general chemistry. We do lots of weak acid calculations in general chemistry. Here we're just going to be mostly concerned with strong acids. Now what's the difference? The difference really has to do with the position of this equilibrium. You put the stuff together, it comes to equilibrium, goes forward and back, and settles down very, very rapidly. At equilibrium, if you have an acid that gives lots and lots of hydronium and has very little of this stuff left, that's a strong acid. The other way around, if you have lots of this side and very little hydronium, that's a weak acid. A gentleman by the name of Bronsted developed Bronsted acid-base theory. Basically, anything that donates a proton in solution is called a Bronsted acid. Anything that can accept a proton is called a Bronsted base. You'll see there's a different nomenclature as well. Well, let's just look at strong acids. Hydrogen chloride is a gas. You can take this gas, dissolve it in water. When you do, it will form hydronium and chloride anion. HCl is a strong acid. So here's our HCl. This is supposed to represent the gas phase. The second this stuff hits water, these hydrogen-chlorine covalent bonds break, and you form only, virtually only, hydronium and chloride ions. 100%. Equilibrium is very, very, very far this way. Now, in reality, this reaction still goes both directions. So, for every billion of these guys that you have, you must have at least one of those. But still, it's basically 100% ionization. For a weak acid, HF turns out to be a weak acid. The equilibrium is going to be such that we have mostly unionized starting material and just a little bit of the ionized, a little bit of hydronium. For acetic acid, that's what this is. The equilibrium is such that you have about 100,000 of these for every one of these. So it's really shifted badly. Acetic acid in water floats mostly around as acetic acid. Every now and then somebody ionizes and goes back, but it's 100,000 we guess. Any questions? Well, the acids we use in lab. Hydrochloric acid is a strong acid. Nitric acid, perchloric acid. For nitric acid, what you basically do is take nitrate, NO3, one negative charge, and you stick a hydrogen on the negative oxygen. Same thing for perchlorate, ClO4, one negative, one hydrogen. These guys all give 1 mole of hydronium per mole of acid. They're referred to as monoprotic acids. Now, the term product refers to the fact that when we transfer this hydrogen from here to the water, it transfers without electrons. So hydrogen with no electrons is what? Just a proton. So that's where the product comes from. Any questions? Diprotic acid. Everybody's favorite is sulfuric. Again, it's sulfate, -2, 2 oxygens, they're hydrogens. Sulfuric acid can ionize in water to form hydronium and hydrogen sulfate. So what we do is we lose one of these guys. Hydrogen sulfate turns out to be an acid. It can ionize as well, and when it does, you're left only with sulfate. This is a diprotic acid, 2 moles of hydronium per mole of sulfuric acid. The only triprotic acid that we work with in lab is phosphoric. Phosphate is -3, so we can put 3 hydrogens on the negative oxygens. Any questions? Well, we discussed a Bronsted acid and a Bronsted base. The Bronsted acid, we said, was a proton donor. Bronsted base was any proton acceptor. In this particular reaction, nitric would be the Bronsted acid, water the Bronsted base. But there's another type of nomenclature that we use that describes conjugate acid-base pairs, just slightly different. In a reaction, the conjugate acid is the Lewis acid. It will donate a proton to something, doesn't matter what, it's a Bronsted base. But what's left over after it donates is the conjugate base. So the conjugate base of nitric acid is just nitrate. Take the proton off, give it a negative charge. Any question? Again, remember this is the Bronsted acid. Bronsted base is an acceptor, but the conjugate base is what's left over after you remove the proton. Let's look at just some ionizations here and identify conjugate acid-base pairs. Here we have HCl, strong acid. It's the Bronsted acid in the pair. The conjugate base of this is going to be HCl minus the proton. We donate a proton to form the conjugate base. So HCl loses its proton to get chloride as its base. Sulfuric acid, we said, did it twice. Sulfuric acid, Bronsted acid, donates to the Bronsted base. What's left over is hydrogen sulfate. Hydrogen sulfate can do it again. Donate the proton, we're left with the conjugate base of sulfate. Now, a Bronsted base typically is going to be water, but it can be anything that can accept a proton in the broadest sense. Here we have nitric acid. This is liquid ammonia. Turns out that liquid ammonia, a very polar molecule, has many of the properties of water. It's even potentially possible that it could support life because of that. If nitric acid donates a proton to liquid ammonia, it will form nitrate anion. Conjugate acid-base pair, this and that. Now, one year I put this on an exam. I was feeling adventurous, but I didn't put it this way. I gave the reaction looking just like that, but I said, identify the conjugate acid-base pair for the reverse reaction. That is, going that way. Now, the rules are still the same. What you do is you look at this side now and you say, what's the proton donor? Only thing with protons is ammonium. When it donates its proton, what's left? Ammonia. So the conjugate acid-base pair for the reverse reaction, ammonia and ammonia. Any questions? Well, there's a tutorial for this. Conjugate acids and bases. Basically what you have are blanks that you type into. Follow the same order for the things. And what you're supposed to do is type in the conjugate acids and bases to complete the equation. So, as we look at this, we see fluoride is our first one here. Fluoride anion. It's obviously a conjugate base of something. So, what's the conjugate acid of fluoride? What loses a proton to give F minus? HF. Over here we have hydronium. What accepts a proton to form hydronium? Water. That's it. Do another. Here we're given reactants. We have chlorate plus hydronium. So the first question is, if we donate a proton to chlorate, what do we get? When it gains a proton, it's simply chlorous acid. When hydronium loses a proton, as a Bronsted acid should, what does it form? Simply water. One more, hydrogen sulfite. and hydronium. Now both of these have protons. They could both potentially be the Bronsted acid. It's going to be the hydronium because otherwise we would form H4O. Doesn't work. So this is going to be our Bronsted acid here. Question is, for hydrogen sulfite, when it gains a proton, what do you get? Simply sulfurous acid. When hydronium loses a proton, what do you get? Simply water. Any questions? Well, being fair, if we have strong acids and weak acids, we should also have strong bases and weak bases. Only makes sense. Only fair. Sodium hydroxide is an example of a strong base. Most strong bases are simply metal hydroxides. This ionizes virtually 100%, but again, it's an equilibrium. There's always a little bit of that left. But it's very little. Now, hydroxide anion from a strong base can react with hydronium ion. When that happens, what do you get? Well, we get water. This is an acid-base reaction. Hydronium plus hydroxide gives water. Now we know something about this reaction because we've seen it before. This is simply autoprotolysis written backwards, isn't it? And we know that autoprotolysis, we have 10 to the minus 7 molar of these guys, so it's almost all water. Likewise, we mix these together, it's going to form essentially all water. Tiny bit of hydronium and hydroxide are always left from autoprotolysis. So, this is an animation to show you what's happening, not really that difficult. Here we have hydroxide. This represents sodium hydroxide. This is hydronium and chloride, HCl, and water. We're going to take this, mix them together. When we do, hydroxide and hydronium will react, and we'll make two waters. And what's left in solution? Sodium chloride. Strong acid, strong base gives us salt and water. This is also worth remembering. If we have equal molar amounts of strong acid and strong base, what we wind up with is simply a salt and neutral water. Any questions? Well, let's look at some old exam questions. Select the pair of substances in which the acid is followed by its conjugate base. Now remember, the acid is going to lose the proton, and the leftovers are the conjugate base. That's an acid, that's not its conjugate base. If we take a proton off of ammonia, we get NH2, not NH4. Here we're adding a proton to hydrogen phosphate. Here we have hydrogen carbonate as an acid, carbonate as its conjugate base. Any questions? Way too many words. The reaction is hydrogen carbonate plus water, carbonate plus hydronium. Okay? Hydrogen carbonate is an acid. That's true. Water is its conjugate base? No. Hydrogen carbonate is still an acid. Carbonate is its conjugate base. Take the hydrogen off here, what do you get? We got B. Let's just look at the rest. Hydronium is an acid. That's not its conjugate base. That's a base pair, and neither is that. Remember, you're just looking for everything except the proton. Conjugate acid of hydrogen sulfate. Question is, if we take a proton, put it on hydrogen sulfate, what do we get? H2SO4. All right, this brings us back to neutrality. So, we took a strong acid and a strong base, mixed equimolar amounts, and we got a neutral solution. Remember, neutral solution still means in water, pure water, we have 1 times 10 to the minus 7 molar hydronium and hydroxide. They're always there. Now, there's something in acids and bases called the pH scale. Way back around the turn of the century, Danish chemists came up with the notion of pH. pH was defined as the negative log of hydrogen ion concentration minus log hydronium. That's pH. This is quite often simply abbreviated as H. The square brackets. In chemistry, anything written inside the square brackets refers to its concentration in moles per liter. So pH minus log hydronium. P simply stands for the term minus log. All right. Again, let's take out our calculators and do the same sort of exercise. If you enter 3,000 and take its log, you should get 3.477. If you then either enter this or just hit 10 to the x, you should be back at 3,000. What's a log? A log is simply the exponent is a base 10 logs. The exponent of 10 that you have to raise 10 to get the number. So if we have 100, that's 10 times 10, 10 squared. The log of 100 is 2. If we had 1,000, 10 times 10 times 10, 10 to the 3, the log of that is 3. That's simple. If we had 316, you could get that as 10 to the 2.5. The log of 316 is simply 2.5. It's simply a way to address the exponent you have to raise 10 to get the number. Now, back when I was a child, the books had long tables. Today, we have calculators. That's a big difference. If you take your calculator and you hit 316 and then log, you should get 2.5-ish. Go backwards, enter 2.5, 10 to the x, you should get 360. One more time. Whenever you see something in square brackets, that's molar concentration. All right. Let's think about our neutral water, okay? We said in neutral water, hydronium was 10 to the minus 7 moles per liter. The log of 10 to the minus 7 molar is 10 to the minus 7. Remember, pH is defined as the negative of that. Therefore, if we have neutral water, the pH is 7. That's where pH 7 comes from. It simply describes the fact that water, pure water, has 10 to the minus 7 molar hydronium. If we have an acidic solution, hydronium is going to be greater than that. Since this is a negative log thing, the pH will be less than 7. Basic solution, we have less than 10 to the minus 7, pH will be greater than 7. Worth remembering, pH is less than 7, it's acidic. Greater than 7 is basic. Any questions? POH, again, if we have pH, it's only fair that we have POH, isn't it? POH minus log of hydroxide. Same concept. Now, in neutral water, hydronium and hydroxide are both 10 to the minus 7 moles. Right? If we took the concentration of hydronium, multiplied it by the concentration of hydroxide, we would get 10 to the minus 14, wouldn't we? Now let's do something that sounds strange. I'm going to take this equation and I'm going to take the negative logs. Hydronium times hydroxide under all conditions at 25 degrees is 10 to the minus 14. If we take the negative log here, negative log of hydronium is pH. Negative log of hydroxide is POH. Negative log here, log would be minus 14, negative log is 14. We get a relationship. pH plus POH is 14. Under all conditions at 25 degrees, pH plus POH will be 14. Hydronium times hydroxide is 10 to the minus 14. Those are worth writing on your little card for the exam. Let's just see how we use this. Here's our relationship. If I tell you that I have hydroxide at 5 times 10 to the minus 8 molar, calculate hydronium. Very simple. We're going to wind up with 10 to the minus 14 divided by hydroxide, and it's about 2 times 10 to the minus 7 molar. If you don't believe it, multiply the two together, you're back to 14. All right, let's stop for a second and let's just think about pH. pH scale. It actually goes below 0 and above 14. These are minus numbers. Those are positive, nonetheless. 1 molar HCl, pH is 0. 1 molar sodium hydroxide is 14. Seawater, blood, sweat, and tears, here somewhere between 7 and 8. Bleach, ammonia, around 12, 13. Down on this end, bad coffee is about 5. Very bad wine, about 3. Stomach acid is about 1.5. It's amazing the stomach just doesn't dissolve itself. It is. How do you measure pH in the lab? Well, in the lab, we would use a pH meter. pH meter is really just a millivolt voltmeter. The business end here is this little probe. This probe has salts on different sides of a very, very thin glass membrane. The glass membrane here is thinner than a human hair. You'll certainly never use one of these, not for a long time in your career. We used to use something very similar to this in the lab at UIC. They were about $2,000 each. When you brought in a new graduate student, there was a training period, right? For about 2 months, you could count on them breaking, 10 or 20 of these, easy. Just slam it down in the beaker, or just touch the side, whatever. So, science is really expensive. This setup is not cheap either. What we use typically in the lab, just for simple measurements, is this stuff. pH paper. Neutral solution, it's green. Put it in acids, it gets redder and redder. Up here in base, it turns purple. So it's a nice, simple way to take a solution and determine if it's acidic, basic, whatever. The way this works, well, it has to do with indicators. Indicators, this is phenolphthalein, it's the common one. In acidic solution, it's colorless. In alkaline solutions, it turns pinkish purple. Some of these have multiple transitions. Somebody was clever enough to figure out what of these guys to mix together to get pH paper. That's really kind of neat stuff. But as clever as we are, chemists that is, the cabbage is to it. Turns out if you take red cabbage and you juice it, you get what we call cabbage juice. Cabbage juice is a pH indicator. If you make the solution acidic, it turns this lovely red. Neutral, we're here at purple blue. And up here in basic solution, it's a disgusting green. Now that's important to know. First of all, cabbages did it first. Secondly, if you happen to cook, red cabbage could be very good. If you take it and you just saute it up neutral, you get the blue purple color. That's good. If you want to be a little exciting, you take and add some vinegar. That makes it acidic. You get lovely red. If you want to really be disgusting to your guests, you take and add a bit of baking soda, and you get disgusting green. Yeah. But these are good. Any questions? All right, indicators are used in what are called titrations. Again, titrations are a general chemistry thing. You use what's called a burette. Burette has a stopcock, so you can turn the fluid on and off. And this is a scale in milliliters. In the titration, you will put in a solution where you know the concentration here. So let's pretend this is an alkaline solution, and we know its molar concentration. In our beaker, we have an acid that we don't know its concentration. We know its volume, but not the concentration. We add some indicator. The indicator we would use would be phenolphthalein, no color, and acid. Then you very carefully and slowly until the indicator changes. Now, you look at your burette. You started here at 10. We ended in this hypothetical thing down at 25.6. Subtract these two. We already knew the concentration of this, right? We now know the volume of this. If we know the concentration and the volume, we know how many moles we added. If you know how many moles it took to neutralize the acid, then you know the concentration of the acid. Simple titration. Any questions? All right, you do this what's coming. We take our pH meter, stick it in a solution. It reads 7.23. What is the hydronium ion concentration? Well, we know that pH is minus log hydronium, right? Having a negative sign there is a little bit bothersome. Let's just multiply this whole equation by -1 to get the negative to this side. So minus pH is log hydronium. Now, we are going to take the antilog of this equation. Antilog. Remember we said that the logarithm was just the exponent of 10. So the antilog of minus pH is simply 10 to the minus pH. The antilog of a log is simply the number. And we get our first very important equation. 10 to the minus pH is hydronium. So let's substitute. Our pH is 7.23. 10 to the minus 7.23 is hydronium. Now again, there was a day when you would then open the back of your book. It would be roughly ½ an inch thick. And you would flip through there looking for 7.23, determine its log, and you would get hydronium. Now, you just pull out your handy calculator. What I would do, 10 to the x here is that, so I hit the green and that. So type in minus 7.23, hit that, I get 5.88. Times 10 to the minus 8. By George, I have just calculated the hydronium ion concentration. Again, the key equation. Write down on your card or the back of your hand or somewhere. 10 to the minus pH is hydronium. Let's just do some problems. If I tell you the pH is 4, what's the hydronium? It's simply 10 to the minus pH. These are integer numbers, so that's so simple. That's simply 10 to the minus 4. Well, the same thing. 10 to the minus 12. Now, we need to figure out 10 to the minus 5.5. And it depends on your calculator. I would enter minus 5.5, hit 10 to the x, 3.2 times 10 to the minus 6. 0.32. Simply 10 to the minus 1.32. 3.8 times 10 to the minus 2. And this one, in the lab at USC, we used to read these values to that precision. That's why they're $2,000 a piece for the little quiz. Simply 10 to the minus 7 point whatever. And that's our hydronium ion concentration. Any questions? Now let's just see if we remember which of these solutions are acidic. Acid, pH is less than 7. Basic, it's above 7. Oh yeah. Acid, base, acid, acid, base. Any questions? All right, you know we're going to have to do this backwards, right? If I give you hydronium, what is the pH? Again, pH is the negative log of our hydronium ion concentration. So, what I want to do is take my hydronium ion concentration from here, type it into my computer, calculate it. Then I hit the magic log button, and I get minus 6.15. Well, that's a minus minus, that's a plus, and that is our pH. Simple as it can be. Any questions? Well, let's do the set. One times 10 to the minus 4, you can do this in your head. It's a nice even number, right? Then take the log of 10 to the minus 4, change the sign. 5 times 10 to the minus 4, type that in, hit the log button, change the sign, 3.3. 1.371 times 10 to the minus 8, type it in, hit log. Sorry, change the sign, 7.86. Now again, see this number? I put that on an exam and simply ask this very simple question. Is this acidic solution or basic? I thought everybody would get it right, of course. Almost nobody did. There were just too many sevens here. Everybody said it was neutral. No. Type it in. We get 6.15. Change the sign. This is acidic. It's below 7. 1 times 10 to the minus 7 is neutral, not 7. And finally, same thing here. Type this in, hit log, change the sign, 4.336. All right, 2 more tutorials coming up. I call them pH 1 and pH 2. pH 1. What is the pH if hydroxide is 6 times 10 to the minus 11? Well, what you're going to have to do here is convert hydroxide to hydronium. We can do that because we know that hydronium times hydroxide is 10 to the minus 14. So we'll take our 10 to the minus 14, divide by hydroxide, and get hydronium. 10 to the minus 14 over this gives that, and then we're going to take its log and get pH. So here's our calculation. We're at 1.6 times 10 to the minus 4. Take the log of it, 3.79. Another one. Here we know hydronium, we need POH. Same thing. You're going to take 10 to the minus 14 divided by this. That will give us hydroxide. Take its negative log. Ten to the minus 14 divided by hydronium is hydroxide. Negative log POH. Negative log of 3.5 times 10 to the minus 12, 11.16. pH 2 is a table. Kind of a neat tutorial, I think. Randomly, you are given one of these, and you type in the rest. So, randomly, we were given pH. First thing I would do is I would just say, well, POH is going to be 14 minus that. 14 minus 10, 11, whatever, 3.17. Now, if we know pH and POH, 10 to the minus pH is hydronium, and 10 to the minus POH is hydroxide. Do one more. Here we're given hydronium. We know that 10 to the minus 14 divided by hydronium is hydroxide. Then we simply convert these to pH and POH. 10 to the minus 14 divided by hydronium, 8.13 times 10 to the minus 12. pH is simply the negative log of this. The OH simply the negative log of this. Now that works very nicely, unless you happen to be on Blackboard. Blackboard, different story. Problem with Blackboard is you can require numeric entries like this, but you cannot put plus or minus values for rounding errors and slop. And that makes it virtually impossible to do these. So, what I did is I did this. You're given a series of numbers. One of these numbers is wrong. Simply tell me which number is wrong.
Which number is water? Is that what you said?
No, which one is wrong?
Oh.
Wrong. So, how do you do that? The way I do it, first thing I do, we have a value for pH and POH, don't we? We know that pH plus POH is 14. Is it? If it's not, and one of these is wrong. So we look at them. 8 plus 8 comes out to be 17-ish. One of them is wrong. So, take hydronium. Going to take its negative load. We get 815. That means that this guy was wrong. Take hydroxide. Get POH, 5.85, not that. This is what you would enter on blackboard. So just follow the very simple steps, step 1 and step 2, and figure out which is wrong. All right. In one form or another, I put this problem on exam 2. Okay, that's a hint. It's as simple as it could be. Here we have cheap red wine, pH at 2.85. I assure you, you do not want to drink this. Can we calculate concentrations of hydronium hydroxide and POH? Hydronium, 10 to the minus pH. We're given the pH of 2.85. Simply do 10 to the x, 1.4 times 10 to the minus 3. Very acidic one. All right, POH. We know pH, we know that the sum of the two was always 14. So let's just do it that way. We know pH. POH is 14 minus 2.85, 11.15. And hydroxide, you can do hydroxide using 10 to the minus 14 in this, or simply take this and do 10 to the minus POH. They both work, they're both simple. 10 to the minus 11, 7.1 times 10 to the minus 12 molar. All right, that is chapter 8 and everything you ever wanted to know about pH. Here's our tutorial list. We've added 3 today, pH 1, pH 2, and conjugate acids. Remember, we're after 350. Even if you have 350 now, you still have to take exam 2. Remember that after we do chapter 9, if you don't happen to have 350 points right now, amnesty weekend, Friday, Saturday, and Sunday. Shuts off Sunday at midnight. Tutorials from the first half and quiz 1 will both be eliminated. Any questions? All right. Have a good day. I will see you Wednesday for lab number 8.